I'd like to welcome everyone to this session on Spatial CONUS-wide Imputation of FIA tree and fuels data in the TreeMap and FuelMap datasets. My name is Laurel Sindewald. I'm an ORISE postdoctoral fellow affiliated with the Missoula Fire Sciences Lab, and I will be serving as the session moderator. We have 90 minutes for today's session and 6 presentations, so it's a full docket. Each presentation will be allocated 15 minutes, during which time the presenters may take questions as time allows following the conclusion of their presentation. In this session, we will hear about updates to the TreeMap and FuelMap datasets, as well as some spicy cutting-edge applications. So if you're new to TreeMap and FuelMap, you'll be getting an introduction from Karin Riley, research ecologist at the Missoula Fire Sciences Lab. Without further ado, let's get started.
All right, I will take it away then, Laurel. Thanks for the intro. So we're going to just start with a brief tour, if my PowerPoint will cooperate, of TreeMap and FuelMap and updates we're making to them. So this is the first time we've talked about TreeMap at one of these FIA symposiums, and I think it's long overdue because we've been working with FIA data since probably about 2011. So we're happy to be here today. It really takes a whole team of people, including the ones you see on this slide, and even more to get the TreeMap data set and the FuelMap data set produced and validated. And it's really been a great, I think, a three-way collaboration between FIA, folks that we work with at GTAC, and then the Missoula Fire Sciences Lab. Okay, so I'm going to start off by talking just a little bit about what TreeMap is, and we're going to have kind of a whirlwind tour of the methods today. This is what the output looks like, for starters. Basically, what you're seeing is a colored pixel for each of the forested pixels in the continental US. And each of those is symbolizing a FIA plot visit or plot CN that's been assigned to that pixel. That's the main output of this data set. And from that FIA plot identifier, you can make yourself a tree level rendition of the US forests. So we're zoomed in there at the lower left. We're zoomed in on a corner of the Mogollon Rim in Arizona, with, again, each of those unique colors being a unique plot visit. And you can see how they kind of cluster into little stands. And here they're kind of clustering along the elevational gradients. That's just kind of resulting from the similarity in those predictor variables at nearby pixels. There's a lot of different ways you could create a data set like this, but we decided to use FIA data, which is, of course, why we're here today, because it's nationally consistent and it has a standard fixed radius plot design. It's also publicly available. And then we also decided to make this data set so that it could really play in the same sandbox with a bunch of our fire modeling software, since a bunch of us are from the fire lab. So we chose to use land fire landscape data as some of our inputs. That, again, is a nationally consistent and publicly available data set. It's also what we use for our fire behavior modeling. So you can see the map at left there is from FSim, the large fire simulator. And that's showing you burn probabilities across the continental US. So anywhere we're in blue there, that's an area that's less likely to burn. Anywhere that's in the oranges and reds, that's an area that's more likely to burn. So the goal of the project here is to take the really detailed measurements that we have at FIA plots. We know a lot about each and every tree on that plot, as well as a lot of the fuels, many different attributes measured at those plots, of course. And we want to assign those really detailed measurements across the landscape. So the landfire grids tell us a little bit about the landscape, but not with much specificity. So we want to fill in the detail that we get from the FIA data. So there's basically 2 inputs that go in here. The FIA plot data, the detailed data, is called the reference data. And then the data we want to assign that to is that gridded landscape data. It's called the target data. So this is just a really super simple example that if you only had 2 plots here and you were assigning those to the center pixel, you can see plot number 1 is going to be the far better match. For example, those are both ponderosa pine. So the output, again, is just a gridded map of those forest plot IDs. We use the YA impute package in R, which is a modified random forests package. And one of the things that random forest needs to run is you have to have the same list of predictor variables available for both your gridded target data and for your plot level variables. So this is the list we came up with for our model. We use location variables, topography, vegetation, biophysical variables, and disturbance variables. One of the reasons for giving this presentation today isn't just to tell you what we've done in the past, but to tell you about the 2020 and 2020 data sets, which are coming soon. And I think one of the exciting things that we've updated here is we've gone from using some biophysical variables that came from Landfire. They were maybe a little spotty on the way that they were documented, and we've gone over to using biophysical variables from DayMet. So Scott Zimmer on our team has summarized those for us. So this is another toy example of how this imputation works, because we do it differently than a lot of folks who are using random forest, so it's worth showing. So for random forest, we're making a model for each of the 67 land fire zones that are in the country, and we have 300 decision trees. There's 75 for each of our response variables. The model is trained on the FIA data, so we go ahead and we build this forest of decision trees based on the FIA data. And then when it's time to run the imputation, we're taking the observations from each pixel. Those get passed through the decision trees. And then what the model is doing here, we're not trying to model an attribute like, number of live or dead trees or carbon. What we're trying to do again is get the most similar plot. So what the model does, it looks in that terminal bucket where the pixel ended up, and it looks to see what plot is in there the most with that pixel. So in this case, it would be 12. That's the only plot that was in both of those buckets. So we would assign plot 12 to pixel number 1. So this is what TreeMap looks like if you download it from the Research Data Archive and you're going to use it in a GIS. Here I've displayed it on that plot identifier. So that's what you're seeing in the window there. The raster also comes with an attribute table attached to it, courtesy of John Shaw. He's pre-calculated a lot of different variables and pre-attached a lot of different variables that we think many users would want to use. So you'll see things like the stand size code. I'm not sure if you can see my pointer, but I'm pointing to the stand size code. There's also live and dead trees per acre and carbon and biomass variables. So I want to take a little bit of a deep dive into using TreeMap to map forest attributes. So I'm showing you here a map that Scott Zimmer's made for us. It's from our yet to be released 2020 data set. So you're getting a little preview here showing the imputed forest type for a section of the Willamette National Forest. And one of the reasons I want to draw attention to the forest type is that in the past, users have alerted us that they have seen some species assignments in there that do not look like they should come from the area. So we've dubbed this the ride-along problem. So you'll see that in the 2014 and 2016 versions of the data set. And if you look at the way the model works, these assignments actually were technically correct because they were coming from the correct existing vegetation group, but there were some kind of strange downstream effects of that. The existing vegetation group can be really broad. So a plot from Minnesota, for example, can assign to Oregon. So we saw some balsam fir plots in Oregon. Generally, these assignments that have the kind of out of area species only affect about 0.3 to 3% of the pixels in an area. But I am here to tell you they can be really disconcerting for users because I get a lot of emails about this. So we've tried a fix for this where we tried restricting plot assignments to only plots that appear in the zone being imputed in adjacent zones. And we also created a master list of all species present in the zone from looking at the FIA plots. And we restricted eligible plots to those with only species on the list. So let's see how this worked. One of the things that we did to see what the effects would be on the model is we compared the imputation with and without the ride-along fix on 100,000 random pixels that appeared in each of the land fire zones. So what we found is with and without that ride-along fix implemented, we had the identical plot assignment in about 60% of the pixels. I was kind of concerned how much this ride-along fix might reduce the number of plots that were imputed in a zone, but we saw that number only decreased by about 3%. And we're probably eliminating the plots that we really don't want to be in there in the first place. So this seems pretty successful. I was also concerned about the effect that this would have on accuracy in the data set. And so I've shown you what happened to accuracies for our 4 response variables down there at the bottom. And we're seeing that they did decrease, but it's just ever so slightly by less than 1%. So that's probably worth it for getting the species right. So let's look at a few graphs of forest type here from the Willamette National Forest, just to make sure we're eliminating the things we really want to eliminate. So this is the percent of the Willamette National Forest that was in each of these forest types at left in the 2016 imputation and at right in the 2020 imputation. And these look fairly similar. Thematically, they are pretty similar. Some of these differences also are going to come from the underlying land fire data and how they classified the vegetation types. But things looking pretty similar here. So shown in these plots are forest types that were more than 0.5% of the area, but where we start to see things get kind of different is when we look at the forest types that just imputed to a few pixels. So this is forest types that imputed to less than 0.5% of the area. This is in the 2016 data set, and you can see like there's a boatload of different forest types here. And we've had Rachel, who's our resident expert, go through and say which types are probably inappropriate. I've drawn a red arrow to those, and there's a couple that are kind of questionable as well. So we're seeing 23 inappropriate forest types and 2 questionable ones in the 2016 imputation. But really, when we total these up, it's not much of the total area at all. It's 0.3% of the total area. Let's see what the ride-along fix did. Looks like we have a much shorter list of forest types here, and a lot of the ones that were inappropriate are gone. So we went from 23 down to just 2. And now the area that has these kind of suspect forest types on it has gone down to 0.017%. So really just a dusting and a sprinkling of pixels out there. I'm going to move us over to talking about FuelMap for just a moment. FuelMap is a companion data set to TreeMap. And the reason we created this is we're starting to do a lot of work where calculating total biomass is important and estimating smoke emissions is important. And so for that, it's really essential for us to be including litter, duff, and woody debris loading in our calculations. And so you might say, well, why don't you just get those from the Plotzians that are imputed in TreeMap? And the reason, for those of you who know your FIA trivia, and I know you're out there, is that FIA collects fuels or down woody material data on only a subset of its plots. So that means there are a whole bunch of Plotzians imputed in TreeMap that do not have down woody material information to go along with them. So what we realized we needed here is we ran a second random forest imputation, super similar to the one I just told you about. It's the same list of predictors and the same way that we've implemented random forests. But what it's doing is it's looking at the list of plots that have the DWM and fuels measurements. That's how we train the model. Then we take any plots that are missing those measurements and feed them through the random forest model. And the model is able to tell us the most similar plot visit that did have the DWM measured. So the output's really super simple. It's just a lookup table, obviously a bigger one than I showed you here because it probably has 60,000, 70,000 different values in it. But at right is the TreeMap Plotzian, and then at left is the one we've identified for FuelMap that's the most similar. So really simple from there to link it over to the TreeMap raster. I'm showing you the FuelMap data set right here. And if you look in that attribute table, you can see the loadings for things like CWD is coarse woody debris, FWD is fine woody debris, and then the duff and litter carbon as well. So for validation, this is a bit of a challenge. The scale at which DWM varies is probably not adequately captured by the transects in the model. And so if you envision here, for example, if you had one big tree fall down on your plot, if it fell across the transect, that's going to give you a really big loading of coarse woody debris. If it fell down next to the transect, you're going to be seeing a much different number. So instead of looking at that pixel value, we're using a set of validation plots from FIA not used in the imputation. And then we're just comparing the distributions that we see in the FIA plots to what we see in the FuelMap data set. So this is just a sampler of 5 different ecoregions. We used some pretty broad ecoregions. There's 20 of these EPA ecoregions in the US, so they're pretty large. But we're comparing FIA plots within those to the distribution in FuelMap, and you can see those compare pretty favorably. This is just a quick peek on what it looks like if you generate a map of litter carbon from FuelMap. And then I just want to say a thanks again to all of the collaborators, includes quite a few folks. And I want to point you to resources for TreeMap and FuelMap. There's a project page that's on our Fire Lab website. There's also the 2016 and 14 data sets and methods papers for TreeMap. And then the FuelMap data set is in the research data archive as well. And hopefully I've left us just a moment for questions, but Laurel can tell me.
Wonderful presentation, Karin. Thank you. I think actually we better keep on moving. It's 3:16, but we might have time for questions later.
And the chat is good for that too.
Yes, there's also, yeah, room in the chat. So next we're going to hear from Rachel Houtman, who's a biological scientist at the Missoula Fire Sciences Lab as well. And I'll go ahead and turn it over to her to present on an analysis ecosystem using TreeMap and FIA data together in FES.
So, hi, thank you for your interest in the work that we've done to create this CONUS-wide tree map that is compatible with the Forest Vegetation Simulator and its Fire and Fuels extension. All right, so let's just jump right in. We have some really powerful data sets here and models that when they fit together, they essentially create a situation where we can not only map variables at the CONUS level in the lower 48 states, but we can also map them with different management options, with different fire options. So what we've brought together is FIA plot data with Landfire. So Landfire is another Forest Service product that provides wall-to-wall mapping in both the CONUS area and Alaska and Hawaii and outlying areas as well, of everything from vegetation type, vegetation height, vegetation cover, fuels. It's a wealth of information. So those data sets we brought together, Karin just went over this. So for anybody who missed the first talk very briefly, those data sets came together with the random forest imputation in the YA impute package to create both the tree map and the fuel map. And the one of the biggest powerful pieces here is that the tree map, by putting plots on the landscape, we can actually put the information that's required to run the forest vegetation simulator together, run that FBS simulator, and then anything that we get out of FBS, we can map back to our landscape. So that's the talk in a nutshell today. If you understand all that, you're free to go, but please don't. All right. So like I said, we've got the forest inventory and analysis data, the Landfire data. The FIA, I think Karin mentioned this, provides high quality, nationally consistent direct plot measurements across the United States. And then the Landfire provides that wall-to-wall 30-meter resolution raster of different landscape attributes. And then we can use those characteristics that occur in both data sets along with those biophysical attributes that Karin talked about to impute the FIA plots to all the points in between plots. So all those unmeasured plots, all those unmeasured areas. All right, so we end up with this TreeMap data set and the FuelMap data set. TreeMap is a CONUS-wide data set. Sorry for repeating, but I always say repetition is how we learn. TreeMap is the CONUS-wide data set of FIA tree records at the 30-meter resolution. We have the versions for 2014 and 2016 available on the Research Data Archive currently. As Karin said, we're validating those 2020 and 2022 data sets. And then we also have the version that's 2016 that's available on Google Earth Engine. Part of the reason that these data sets were created was to estimate the risk of wildfire to forest carbon. And so since only that subset of FIA plots include those fuel transects, FuelMap was created to impute fuels to those plots that didn't have those transects. With regards to FBS, so tying that all together, that creates an input for those fuel categories rather than resorting to default settings within the model. I actually ran tree maps through FES originally without FuelMap data, and it dramatically underestimated in parts of the country how much fuel there was compared to once we actually input the FuelMap data. Someday I'll put some tables together showing that. So for anybody who's not familiar with the Forest Vegetation Simulator, FES is a Forest Service maintained individual tree-based forest growth model. It's comprised of 18 geographic variants plus Alaska. And it's free and open source. And one of the really great things about it is if you want to learn how to use it, anybody who has used FES knows that it can be a little quirky, but if you want to learn how to use it, this training modules and support options are really extensive. And I will say that the FES support people have heard a lot from me over the years, and I appreciate every time that they are able to get back to me and answer questions and solve problems. So FES requires a stand table and a tree table for every stand. So you get information about the stand itself, and then you also get information about every tree that's on that stand. You get a length of the simulation, so you might want to simulate it for 5 years or 100 years, and then you define those desired outputs. There are other inputs as well, but those are kind of your most basic. FES models growth, mortality, and decay, and then it also can do management options and disturbances. So it makes it a really powerful tool for local and landscape level planning. I'm just going to keep moving the faces around. All right, so let's talk about how we go from FES, from TreeMap stands to FES, and then we'll talk about how we can map it back as well. So TreeMap, this is the map that Karin had up in her, or a similar map to what Karin had up in her presentation, where we have each pixel mapped to, each plot has a pixel, each pixel has a plot mapped to it. And then in FES, so I call this kind of system required stratification. So in FES, we're gonna, if we have a plot that exists in multiple variants, we're gonna simulate that plot individually for each variant. And then the same for locations, potentially. You might also want to break it out into the specific location where that plot is found. So what we end up with by overlaying this is a set of, we start out with, I should have gotten this number. It's less than 100,000 unique tree map plots from FIA that go into this original tree map. And then when you overlay that with variants and locations, you end up with either, if you're just doing variants, 144,000 unique combinations. And if you're doing variants and locations, you have over 500,000 simulations. So simulations for a single scenario. So if you wanted to then run multiple scenarios through FES for the whole country, you would have to run, say, if you wanted 2, you'd have to run over 1 million scenarios. When I've done this and I've run 144,000 scenarios in the old version of FES, it takes me about a week on my very small laptop. I'm really excited to try running it on my very powerful new computer. So a little bit more about how we actually then run FES. So here are our inputs. I talked about the stand list. Sorry if this is so small. So in the stand list, we have our stand CN, which is our control number. And those are those unique combinations of plot CN plus variant plus location. So that gives us a tie back to that map. I call it a key. Then we also have our stand IDs. So the stand ID itself is the individual stand type, and that ties back to our tree list. So we've got our unique stand identifier, and then we have the tie between the stand list itself and the tree list. And just a note that we also have, here's where we see those fuel attributes as well. So these are our basic stand attributes, but then we also have those FuelMap attributes that are populated when we join that information in. All right, so running FES, we have 2 options, and I'm looking at my time. Okay, running FES, we have 2 options. We can either run FES online, which is a user interface produced by the FES folks who you can download the program, and when you run it, it opens up in your browser. It actually runs on your machine, but that interface is online. It's great for users who have, and I shouldn't say just minimal experience, but it's great for users who either have minimal experience or just learning the program. But it also works really well for small projects or projects where you're not running like 10 million instances of FES. So when I'm running national level FES, I've been using an R script that I had written myself for using it with Access, but FES has since updated to SQLite databases or SQL databases. And thankfully, the FES folks have also put together an R package that allows us to run FES directly with those SQL databases. So the other option is to use that R package and loop through running. Currently I use what I think Karin has called the poor man's parallelization, where you just run multiple instances at once. And I'm interested in figuring out ways to make that run faster. But I did run a small subsample, and it looks like it runs in about 1/10 the time that it was when it was dealing with Microsoft Access. So, and then we get to the FES output. So this is the meat, right? We're trying to get these FES outputs so that we can see differences on the landscape. We can map things to the landscape. And so everything that you see here in this list, these are all tables of outputs that are available from FES. So you can get anything from snags to mortality to carbon. And I'll talk more about carbon. I think Karin's going to talk a little bit more about carbon in a few minutes, and then I'm going to talk more about carbon after that. So we'll hear more about that in a little bit. So here's our map back. Now we've run FES. We're going to join it back to the original table, and then we can create the original raster, and then we can create rasters from those outputs in FES for CONUS. So this is using the lookup function in ArcGIS. You can create these rasters. I will warn you that if you are creating these rasters and actually saving them, you will destroy your hard drive very quickly. It's good to have an extra external hard drive.
Hey, Rachel, just 1 minute warning.
Oh, okay.
Sorry.
No, thank you. I'm just about wrapped up. That's perfect timing. All right. So when I was talking about the system required stratification, there's also the stratification of managers, right? So we might want to we have a manager who wants to treat stands differently in compartment 1 versus compartment 2. So in the same way that we can stratify our landscape for system requirements, we can stratify our landscape from using management designations. So in this case, we have compartment 1 plots that are in both compartment 1 here and in compartment 2. And what we do is exactly the same thing that we did with the variants and the locations. We can stratify those plots using that compartment designation. All right, and I'm just going to fly through that. So again, next steps, TreeMap 2020 and 2022 are currently in the validation process. FIADB, a caveat is that FIADB does contain FES-ready data tables, but the tables don't currently have FuelMap plots populated for those plots without fuel transects. You can, if you're SQLite savvy, you can create those yourself, but just a heads up that those aren't in there. And then finally, each project should be explored for coverage. I'll talk a little bit more about that in my next talk. In limited areas, TreeMap 2014 misses forest cover due to some definition uses used by Landfire for existing veg. And I will leave it there.
Awesome. Thank you, Rachel. I also loved the teeny tiny thank you that popped up at the end. That was a nice touch. Okay, we're going to turn it over to John Shaw. Oh, nope, sorry. We're turning it over to Karin again. Karin is going to speak on quantifying carbon risk and smoke emissions using TreeMap, FES, and the large fire simulator, FSim.
Okay, so for those of you who have been on for a while, you're starting to see some themes popping up here. These have to do with TreeMap, FBS, and some fire modeling, and these themes are going to come out for the rest of this session. So collaborators on this talk on carbon risk are myself, Rachel Houtman, Kevin Young, and Mark Finney. So I wanted to start off with a slide about why this is even important. And I'm sure there are a lot of reasons that I don't even have on this slide, but some of the ones that I think come across our desks really often is that carbon analyses are now mandated as part of NEPA for national forests. So we've been hearing from some national forests and regions. Also, the private carbon market is a multi-billion-dollar industry, and there may be a need for private landowners to establish risk to their carbon projects. We're also hearing a lot about smoke. We're working with various collaborators on smoke emissions. This includes Nature Conservancy as well. And that's for public health reasons, very important reason, and also complying with state and national air quality regulations. So when you look at this confluence of different needs, we realize that tracking the various carbon pools is of importance. The carbon markets themselves really care about those live and dead standing tree pools. But then if you're thinking about simulating smoke emissions, litter, duff, and woody debris really become of importance to capture in your modeling as well. So let's go through a framework that we use for wildfire risk at the Fire Lab. This is a pretty mature framework by now. It was first published in that publication at the bottom there. I think that was in 2013. And so we use a triangle to describe wildfire risk. The first arm of that is likelihood, or the probability of burning. The second arm is the intensity, or the flame length. And then the third arm is susceptibility. So that basically means the effect of fire on various highly valued resources. Commonly, we got a lot of requests to extend this risk framework to communities and homes, also municipal watersheds. This framework also happens to work really nicely for carbon and a lot of other resources as well. So we talked just a bit about FSim already, but I want to tell you a little bit more about the model because it's really critical for the analyses that we're doing here. That first limb of the triangle, that likelihood triangle, we get from FSim outputs. And so this map that you see here, this is the national level map that we created at the Fire Lab for wildfire likelihood. Anywhere that's in blue is an area that has lower risk of burning, and anywhere that's in the oranges and reds have a higher likelihood of burning in any given year. So let's see how FSim comes up with a map like that. Let's look under the hood just a little bit. There's a number of inputs we give to FSim, including landscape models. We use a static landscape that comes from the Landfire project. So this is maps of things like forest cover and fuel model. We also need weather observations for this model. We get those from remote automated weather stations, or we can use gridded sources like GridMet. And then we also need fire records that we get from Karin Short's fire occurrence database, which is a really nice compendium of fires on all lands around the country. We also need fire containment records to tell us about fire duration and when fires tend to go out. So we get those from the ICS 209 reports. And then FSim kind of goes to town on this with a bunch of different components under the hood there. We're simulating 10,000 or more years of different fire seasons. So there's a module in FSim for weather, and that generates a bunch of hypothetical fire seasons for us. We also generate ignitions, fire spread, and fire suppression. So basically FSim is generating, it's simulating individual small fires and millions of those when we're working at the continental level. What you see in that map on the right is the individual fire perimeters for this area in Utah. And if you stack those up, basically the model is just counting how many times each of those pixels burned. So anywhere that's in orange had pixels that burn more often, and in those blues is the less. Then we also get intensity from FSim as well. So as the model is doing all its fire simulations, it's also keeping track of the flame length of the fires. And that can vary for any given pixel depending on what the weather stream is, what the winds were that day, whether the fire is roaring up a hill or if it's calmly backing down. Those are all things that'll give you different intensities for the same spot. So the model records the flame length as well and records how many times the pixel burned at each of those flame length bins you see at the right. So that 0 to 2 foot flame length is going to be something like a surface fire. That 12 plus feet is probably going to be a crown fire. So now let's move on to the third leg of our triangle, or susceptibility. So actually looking at how that wildfire risk translates to forest carbon. And here's where TreeMap comes in. That's what gives us our estimates of carbon. So again, if you're a newcomer to this session, the TreeMap dataset is basically a tree-level model of the forests of the continental US. So we've taken FIA plot visits and we've assigned those to each forested pixel in the continental US. And then the TreeMap and FuelMap combinations, we simulate fires on those plots that you just saw in the TreeMap dataset at each of those 6 flame lengths that comes out of FSim. We do that in the Forest Vegetation Simulator's Fire and Fuels extension. And that gives us what we refer to as a response function. So response function, basically we just mean how much carbon is being emitted or retained on site across those different flame lengths. So this is a toy one I've seen you here. I didn't get it from real data, but they look really similar to this. Even when you're at that 0 to 2 foot flame length, you have quite a bit of emissions coming from that because of the litter, duff, coarse and fine woody debris. And then as you go up in flame length, you're definitely emitting more carbon. But as you see, as you get to the top of that response function, you're just kind of singeing additional leaves and needles off of a tree. So it's not really adding that much. Okay, so we're going to start to wrap this all together here. Again, taking carbon from TreeMap and FuelMap, taking that likelihood leg of the equation from FSim, also that intensity from FSim, and then that susceptibility part of the function coming from our simulations in FVS, looking at carbon emitted under fires of different intensity. So this is a map that Rachel made where we're basically mapping out the carbon released by fire across the continental US. And we've done that for each of these 6 flame lengths. This is the map for the 20-foot flame length. You can see that actually that carbon released by fire in a lot of places where you're seeing the higher releases, that's driven a lot by the litter and duff and coarse and fine woody debris loading. So for those of you that are equation people here, this is looking at this through an actuarial risk framework. This is the same sort of equation that insurance companies use when they're computing risk to homes. So they're going to look at the risk of things like hurricane, fire, etc., and what that might be expected to do to your house. This is the exact same framework. So we actually have insurance companies using this data quite a bit as well. So here we're calculating expected carbon emissions. At left there, I've put how the likelihood, intensity, and susceptibility go into this function. Basically, what you're doing here is you're taking the probability of a fire at each of those 6 different flame lengths, and you're multiplying that probability by the amount of carbon that you predicted to be emitted in a fire of that flame length. And then basically you're summing across those different flame lengths. And then if you're working at the landscape level and not just a pixel, you're also summing this across pixels. So if you want, for example, to estimate carbon emissions coming from a national forest, you would sum this across all the pixels in that national forest. So let's take a look at what this looks like for an individual property. This is an improved forest management project that's in Northern California, and it kind of helps to zoom in here. I'm going to do a little time check, Laurel. Okay, looks like I'm doing pretty okay so far. So we're going to spend a little time on this slide because we can. There's a lot to look at here. So if we look at this center panel, you'll see at that lower right, there's the annual burn probability for that parcel. So in the southern part of that property, that area has a higher probability of burning than the northern part of the property. And then just above that panel is the initial carbon in tons per acre. You can see that kind of varies across the project, with those yellow colors being the areas with more carbon. And then if we go to the left, this is where we have actually started to put all of this data through that response function and through that equation we looked at a moment ago. So this is a map of the annual expected carbon loss from live trees. So if we look at these little scale bars for a minute, you'll start to see some things that are pretty interesting. This is an area that has a fairly high burn probability, but even so, it's maxing out at a probability of about 0.02. That's considered a fairly high probability. So burning once in about 50 years. Then if you look at the panel at left with the expected annual carbon loss, you'll see it tops out around 0.1 tons per acre. And that's pretty different than the initial carbon estimate that is there. That tops out at 208 tons per acre. So this is a pretty interesting thing about the risk framework is once you incorporate that probability of burning and you annualize these estimates, you can see those scale bars are pretty different. If we total up the expected carbon loss across that property, we get an annual expected carbon loss around 99 tons per acre. So obviously you're not going to have a fire here every year. Some years that carbon loss is going to be 0. Some years you might have a really big severe fire and it's much larger than that. This is representing our annual averages. And then if you look at the map right there, let's see what we expect from this area for annual smoke emissions. And again, imagining not every year we're going to have a fire, it's going to be pretty variable. But if you look at your annual mean, this is what it would look like. So the emissions are, I think, driven by the pattern you see in both the carbon, initial carbon loading and the burn probability. But interestingly, that annual expected carbon loss here, it's really pretty heavily driven by the burn probability. If you sum up those annual emissions, you're expecting about 674 tons per year. This is probably an area that has a lot of litter and death. So just as a parting shot, I thought I would put this into the analysis ecosystem concept Rachel talked about a moment ago and put it into a flowchart for those of you who like flowcharts and you know who you are out there. So we have those green boxes. That's our TreeMap and FuelMap observations going into the forest vegetation simulator. We can do simulations in there to simulate fires of different flame lengths. And that'll give us estimates of the carbon emitted from fire in various pools and the carbon retained on site after fire. If we move to the flowchart on the right here, these are our burn probability outputs. So you see that magenta box has FSim. From FSim, we're getting our flame length probabilities. And then each of those 3 orange boxes we're feeding into our actuarial risk framework, right? So we have our flame length probabilities and then the carbon emitted from fire and retained on site. So from those, we can derive our expected annual carbon that stays on site and our expected carbon emissions. So I think we have maybe a few minutes left for questions this time. I'll let Laurel tell me. We have a whole bunch of other collaborators, and I want to make sure we're recognizing those. Those are both on the FSim outputs and then on the work that was needed to translate this into carbon units. There's also a big list of resources for you here if you're interested in any of these data sets. So that includes not only the FSim data sets, but the TreeMap and the FuelMap. If you're interested in reading more about that risk framework and how it's applied, I've also put that link there as well.
I think we might have a single solitary minute for questions.
But I've set a record then, since
yeah,
we've had none yet.
There's a question from Nadia. Is there a way to have veg or fire feedback loop, or have a veg or fire feedback loop to then look at how fire probability changes over time in response to treatments or fires modeled in FES?
Well, I feel like I just could have seeded that question. Thank you, Nadia, because if you stay tuned, that is what Shawn and Laurel are going to be talking to you about. We have some bill funding to take that question on, and so we're at the beginning stages of that project.
Awesome. Thank you for answering. Okay, let's see. Let's turn it back over to Rachel. Rachel's talk on nationally consistent methodologies for quantifying risk to carbon and forest carbon projects using TreeMap and FSim.
Okay, thank you. All right. Well, thank you again for being here to listen to what we've been working on. Some of what you're going to hear me again is a recap. I think we've set up these talks pretty well so that we're kind of flowing into each other. I'm going to talk a bit about wildfire risk that Karin just talked about, but with a focus on carbon offset projects. So reducing emissions and capturing carbon using natural climate solutions like carbon offsets is one of the tools that our toolbox for stabilizing, reducing the increase in atmospheric greenhouse gases. In this case, we're going to talk again about improved forest management projects, which store carbon above a calculated baseline. So that baseline is usually calculated by looking at the business as usual approach to management in the general area that the project is located. the carbon that's measured above that baseline can potentially be available for crediting. However, with forest carbon, we also have to consider the possibility that it will burn up, or it will get blown down, or it will be eaten by insects, or there will be a drought and it will die and it will stop growing. So when it comes to forest carbon, the carbon projects not individual projects, but carbon markets create these buffer pools. So it's essentially an insurance against the loss of credited carbon at the systematic level, right? Or the level of the system. Identifying the amount of that carbon to correctly insure against systemic loss, but doesn't overestimate the risk, we have to figure out how to create that buffer so that we're not disincentivizing projects that would provide a benefit, but we're also not underestimating the risk to that carbon. So the first step, and this what I'm going to talk about today, is is understanding how much we're going to expect to lose in a given year. Okay, so just to talk a little bit about the carbon projects we're looking at. So this is the compliance market from CARB. These are publicly available data sets. There are 113 compliance projects. I think there are actually more than that now, but when we pulled these projects, that was what we were at. And then 35 of those projects overlap with the 2014 TreeMap data set. And that's going to be important because we're gonna compare some of the TreeMap data with those carbon project data. Projects only, an important point with carbon markets, that projects only counts with quote unquote stable carbon. I've heard other people call it persistent carbon or resistant carbon, which is that carbon stored in live and dead trees, and that includes the roots. As opposed to, we're not going to talk about, I like to call it ephemeral carbon. So carbon that will disappear in a fire. So when Karin showed the graph showing that, like, even in the 2-foot flame length fire, we still lose, what was it, 40 tons per acre on average or something like that. We still lose a large amount of the forest carbon in stands where there's a lot of duff and litter. So we're really talking about that carbon that's stored in those trees, that's, even if it burns, it has to burn at a really high intensity to have a big impact on that carbon. Again, these projects calculate a baseline carbon, and then those buffer pools are an insurance against disturbance risk. All right, so this is a very quick recap on what Karin talked about. So with projects spanning across the entire United States, how do we measure risk across that landscape in a consistent manner? So a quick flashback to the last talk, wildfire risk is a 3-legged triangle, and we need a consistent methodology for the whole nation. So we've got our burn probability out of FSim. That's our likelihood. We've got our conditional intensity probabilities also out of FSim. So that's our flame length grids, and then flame length probability grids. And then we've also got the impact. So how does the fire at a given intensity impact the carbon if it occurs? So I'm going to pull up the same or a very similar equation to what Karin showed earlier. I'm also going to show you, I am a numbers person, and being able to see what it actually plays out as for a single pixel was really helpful for me. So I hope this helps with that concept as well. So this is a single pixel. This was another project that I was working on, but this shows the numbers for a single pixel. We have the burn probability. See, it's a very, very small for a single individual pixel, right? Because the likelihood that a fire will happen on one 30-meter pixel on the landscape is going to be very low. And then for this pixel, it happened to be that there were 0 low intensity fires that hit that pixel. So nothing in the 1-foot flame length bin, nothing in the 3-foot flame length bin, nothing in the 5-foot flame length bin. And then we did have some fires that hit in the 7-foot, the 10-foot, and the 20-foot flame length bins. So what we end up with is this total expected emissions. In this case, it was a total expected emissions of 0.033 tons per acre for that pixel. And then that's summed across, or that's calculated across the entire landscape. Okay. All right. So back to the question of that national, why is it so important to have that nationally consistent database, especially when you're talking about carbon projects? So carbon offset projects measure their own carbon, right? Because the whole point is that they're trying to sell carbon offsets. They want to know what's there. So in the case of compliance projects, the standards for those measurements are really rigorous. And we wanted to make sure that our TreeMap estimates were reasonable when compared with those project level estimates, because we don't want the projects to be like, well, you said we only had, half the amount of carbon on our project that we actually had. So we did a little comparison of the TreeMap carbon with the total carbon estimates for those standing live and dead pools from the carbon projects. And we found pretty darn good match. So as you can see here, and I realize I am terribly remiss, Kamini Yadev, who's one of our ORISE people, produced this, and I did not credit her. And so I'm verbally going to credit her, and I will fix this slide before I share it. But what we found was TreeMap does a pretty good job. We've got TreeMap here, and we've got the carbon project carbon at the bottom. TreeMap does a pretty darn good job of estimating the carbon when compared with those project level estimates. Our R squared is over 0.94, and we do have a few outliers, and we've been tracking down why that is. I'll talk about that in a second. I did find the very first one that I calculated it, I think 5 or 6 times, because I just wasn't sure that we could have gotten that close. I think it was 1.3% less than the carbon estimated by the project itself. Right. And so one of the questions is, where did TreeMap miss the mark? So when we're talking about this national data set, when we're looking at an individual project, there are a few things that we want people to be aware of. One of them is the tree masks. So in this case, what you're looking at here is a project on the coast of North Carolina that TreeMap missed by something like 48%. We were way underestimating in TreeMap 2014. And so exploring that, it turns out that in the Landfire data set, there was an existing vegetation type. Sorry, I don't have legends here. There is an existing vegetation type of shrub for most of that data set for the 2014 TreeMap. And so we well underestimated compared to the carbon project. Now, I thought, well, how did we do in 2016? There was a remap in Landfire in 2016. And sure enough, it captured that was a forested area. When we looked at the NAPE imagery from 2014, it should have captured that it was forest cover. So it wasn't just that it wasn't forest cover at that point, it was. And so it caught up in the TreeMap 2016. So sometimes there's a little sleuthing that needs to be done when you're working with a specific project. All right. And so in the end, what we calculate is this expected annual forest carbon loss. And I'm going to say carbon loss, right? Because these aren't necessarily emissions. Some of that carbon that was in those standing live and dead trees may have moved out of those pools into forest floor pools. As opposed to when we're looking at total carbon change, that would be emissions, because we account for all the pools when we're talking about total carbon change, which is what Karin had been talking about in her previous talk. So now we have this national map, wall-to-wall expected loss, and you'll see again that those numbers are, and again, I typed in emissions there. I get them. It's very easy to get those incorrect. Ignore emissions in the map. It is loss. And it is very small. Even in the highest loss areas, we're seeing less than 0.5 ton per acre. And again, that's because we know that fire is not going to occur everywhere. Okay. And so let's look at that at the project level. So here, I'm very sorry, this is so tiny, but I hope you can see a bit that there are projects in the Northeast that are the lowest, projects in the Southeast that are the lowest category here. And then we see as we move to the West, where we would expect to have a higher fire risk, we end up with, sure enough, projects that have that per acre average expected loss that increases for a given. So this allows us to compare the risk across different projects of different sizes, as opposed to, and this is at the same time, each project is going to want to know how much carbon they're expected to lose in a given year for that buffer pool. And in this case, we sum that expected loss over the area, and we end up with our highest loss down here of upwards of potentially 623 tons total. Or remember, that is still an average, an annual expected loss for this project down in New Mexico. But we see that same pattern where projects in the East and the Southeast are less likely to burn from wildfire, and projects in the West are more likely, essentially. Okay. So what are our next steps? Continuing to understand those differences between TreeMap and carbon project estimates. So we could also, there were a couple of cases where when we saw the carbon measured in 2014 in TreeMap and the carbon that was reported in 2015, say in a carbon project, and the project burned between those two reports, there's some differences there. And we're still exploring other possibilities for some of those outliers. Identifying and modeling management actions that could reduce wildfire risk to carbon. And I think that sets up Laurel and Shawn for some of those questions. Modeling specific changes in risk from management. So that involves moving back to that FSim output and determining how different management actions could impact those FSim probabilities, and then incorporating the impact of wildfire mortality on carbon projects over time as well. So this doesn't account for the fact that some of those trees move from live carbon into dead carbon, and how does that impact their projection in terms of the timeline for their carbon storage. All right. Thank you. And I don't know that I have time for questions, but I'll leave that to Laurel.
Thanks, Rachel. Thank you for your talk. That was great. It looks like we just hit 4 p.m. Mountain time, I guess 3 p.m. Pacific time. So we might need to keep moving. Okay. All right. So next up we have Shawn Urbanski, who is a research scientist at Rocky Mountain Research Station and Missoula Fire Sciences Lab. He will be speaking on wildland fire emissions trade-offs.
So welcome, everyone. First, I'll start off with a little bit of an apology here. If you were looking forward to my talk, you see that there's a big title and topic change on this. And this was because my presentation and the one that Laurel will be giving following mine, what I originally planned, there's a lot of overlap between those two presentations. And rather than duplicating a lot of material, we decided to make our presentations complementary, a part one and part two, if you will. So what I'm going to do is I'm going to provide an overview of a modeling and analysis framework that we're developing for quantifying the potential impacts of prescribed fires and fuel treatments on future wildfire smoke emissions. And in the presentation following this one, the grand finale for the session, Laurel's going to provide a simple demonstration of how this framework could be applied to inform land management decisions. Okay, so starting off with a little background. The focus in general, the issue at hand is reducing wildfire risk. Is everyone here, as I'm sure, is familiar with, the motivation for this project is a topic that is of top concern for land managers. There's been a significant increase in the frequency, breadth, and severity of wildfires in the western U.S. over the last couple of decades. And reducing wildfire risk to highly valued resources is a top priority among land managers. in the West. And prescribed fire is one of the important tools for helping reduce wildfire risk. Okay, so in fact, there's major efforts are underway to increase fuel treatments, including prescribed fire, across all lands in the West. Many of you are familiar with the USDA Forest Service Wildfire Crisis Implementation Plan, where they're proposing 50 million acres of additional treatments across the West over the next 10 years. I guess we're already 2 years into that, followed by maintenance treatments. And this does include prescribed fire, and smoke from prescribed fire can be a significant impediment to its use, especially in the West. So if we're putting more smoke in the air through the expanded use of prescribed fires, one thing land managers would like to know is, can prescribed fire reduce future wildfire smoke to provide a net air quality benefit? So while improving air quality down the road might not be the primary objective, it's protecting communities or other highly valued resources. At the time the fire is going, land managers would like to be able to say to communities that are impacted by smoke from prescribed fires, okay, you're getting a little smoke now, but it's likely that down the road you're going to get significantly less smoke in the long run. And that's kind of the focus of this project, if you will. Okay, so having laid out kind of the motivation for our project, we haven't really come up with a catchy name for it yet. Feel free to throw one in the chats if you do have one. But the basic idea is giving out land management objectives, for instance, reducing risk of severe wildfire to the community, and possible land management actions, that let's say they assume they include prescribed fire treatments. Our framework, we'd like to be able to address kind of three primary questions. How likely are the prescribed fire treatments and/or mechanical field treatments likely to achieve the primary objectives of the land management of the land managers, protecting a community, for instance? Also, what are the potential smoke impacts from the prescribed fires that are going to be used to achieve those objectives? And then finally, will these treatments reduce the likelihood of severe smoke events in the future? Okay, so this is just a little flow chart here, an overall layout of the framework we're building together. Again, the main question is, how are land managed activities likely to affect future wildfire occurrence and the associated smoke emissions and impacts on air quality? So we start off in the upper left-hand side there, start off with the landscape for which different management actions are being considered, some or all of which may include prescribed fire. Prescribed fire produces smoke, which potentially has air quality impacts, usually in the communities near the fires. So we take those, we modify the landscape with the management scenarios. Then we can use that landscape and we combine it with models of forest growth and regeneration in treatment and fire effects, as well as simulations of future wildfire occurrence. And this allows us at the effectiveness of land management action to address, the effectiveness of land management actions and how their effectiveness degrades over time. And hopefully how is future wildfire occurrence and associated smoke emissions and air quality impacts affected by these actions? Now I'm going to kind of just walk through the different components of this framework. So the initial landscape, I don't have to say much about that. We're using TreeMap and FuelMap, which Karin Riley has discussed in a previous presentation, and that, of course, is based on FIA plot data. In terms of the prescribed fire scenarios, those could be scenarios we're working to develop scenarios with land management partners now, and then also there's lots of scenarios that researchers like to come up with on their own, some realistic, some not. And then we go on to, we're talking about, when we're trying to simulate forest growth and fire effects and the effects of treatment on forests, we're using the forest vegetation simulator, and fortunately Rachel gave a nice overview of that, and that also allows us to estimate smoke emissions. And then the fire aspect of it, what are the future wildfires? We're using probabilistic wildfire simulations, and that's the FSim wildfire simulation system, which Karin has discussed previously as well. So next, I'm just going to do a quick walkthrough of these framework components. Fortunately, the preceding talks have set me up pretty well. Okay, so the initial landscape again. So, land fire, we're using the land data, national data set of vegetation and wildland fuels. For our purposes, it provides terrain, fire behavior fuel models, and canopy fuels as input for the FSim large fire simulator, so we can simulate fire spread and fire intensity. And then the TreeMap and the FuelMap, which is a tree level map of U.S. forests based on imputation of FIA plot data using Landfire. This provides the forest structure and surface fuel loadings. And this is the input for FDS to simulate the effects of fuel treatments and fires, and also forest growth and regeneration. And as I had mentioned, it's also through those fire effects that we get at the smoke emissions. Okay, so a quick overview of the FDS. You probably really don't need to mention this, but I put together the slides, so I'm just going to run through it real quick, since Rachel gave a very good overview of it. So basically, we were using FIA data as input, and that FIA data is supplied spatially across a landscape through TreeMap and FuelMap. And we're using it to, in our case, we're using it to simulate the effects of treatments and fire effects, changes in fuels, tree mortality, smoke emissions, which we get through the fuel consumption that's calculated by FDS, and as well as post-disturbance stand evolution. One thing to note is that FDS lacks regeneration models, and our project is currently developing a regeneration model for our test area, our test study area, which is the Okanogan-Wenatchee National Forest. So on to the probabilistic simulation of large wildfires. So as I mentioned, we're using FSim large fire simulation system. It was developed at the Missoula Fire Sciences Lab by Mark Finney's team. Basically, the system simulates weather, ignition, fire ignitions, fire spread, fire intensity, and the effects of suppression. And typically when you run this, you might run it, simulate ignition and in fire growth and intensity for 10,000 simulation years. We're with each year using a different ignition locations and weather stream. A little more detail on this. Yeah, about half of this looks a lot like Karin's slide on FSim. Thank you, Karin. But again, the input's still the same. We have a landscape provided by Landfire, weather observations, a fire occurrence database from Karin Short, and then containment records. And then in the middle, so FSim is simulating, say, 10,000 plus years of ignitions, weather, fire spread, and suppression. And then in the output, for each simulation year, we receive fire perimeters, a map of day of burning, so we know on which days FSim simulated that a particular pixel burned, which is important, as I'll talk about later. And also flame length. You take those 10,000 years together, and you can look at things like Rachel was discussing earlier, and Karin were discussing earlier about mapping out, say, over a landscape, what's the burn probability or the probability of a high intensity fire, for instance. Okay, so the FSim outputs, so just a real quick on the left-hand side, this gives an example of the FSim outputs. You have something like a map of the burn day and the ignition points, a map of the flame length, which is the fire intensity. Put together 10,000 seasons of those, and you can map out things like the burn probability or the probability of a high-intensity fire. So these are the basic FSim outputs, and they are very useful for land managers. They can help them address questions like, will this land management action reduce the probability of fire impacting a community, for instance? But what FSim alone doesn't provide is information on smoke production, tree mortality, or medium-term effects in terms of, we conduct a fuel treatment. Well, what happened? How effective is that fuel treatment 10 years down the road? We can't really say that specifically with an FSim simulation because it gets the landscape, you give it at the beginning, and it's static throughout that same set of simulations. And so this is where FDS enters. And as Rachel had mentioned, it's a wee bit finicky, but basically we're coupling our FSim outputs to FDS. And I'm just giving kind of a quick diagram to give you an idea how that is. So on the left-hand side, we might have one season of fire simulations, a map of flame length, a map of the arrival date. We feed that into FDS, along with the TreeMap and the FuelMap data that's needed as input to drive FDS. And then calculate fuel consumption. Here I'm just focusing on it calculates many different fire effects, but our focus here is the fuel consumption because we want that for to estimate smoke emissions. And in this case, you can see we can map out smoke, and as I smoke in air quotes, we're focusing on fine particulate matter, or PM2.5, since that's the pollutant of greatest concern in smoke. And so you can see for each season, we can map out the smoke, where it is, when it occurred, because we have the arrival date from FSim. And then you can see also, we can kind of map out, you can see over a landscape, what were the daily emissions over the course of time for that fire season. And this is the kind of information that we need to estimate air quality impacts down the road. Okay, so putting it all together, this is an example of, how am I doing on time here? Okay, a couple minutes. Of how we put it all together for one land management scenario. So, start off in the upper left-hand side, we have a land management scenario. We use FDS to update the landscape. Let's say in this case, it's just prescribed fire treatments. We output that, modify that updated landscape. We run FSim on it, give it 10, 20,000 simulations, feed that output into FDS again, and then we can see we have our products here. And from that, if you look on the right-hand side, you can see how in any given year, so we have at the lower left, on the lower box there on the left-hand side, you can see that histogram. So that would be annual emissions for a landscape over 10,000 years. So what we're interested in perhaps is say, so what are the chances that we have a really severe smoke impact, say those top 10% of years or 5% of years. So we can pluck out one of those 5% of years and look at the daily emissions from that, and it can be handed off to an atmospheric model to simulate air quality impacts within near the fires or within regionally. And then on the top there, I'm just showing how one can go through and we could subsample. So we've done 10,000 simulations, subsample, and then those landscapes, how they've been affected, see how the fire impacted them, doing FDS simulations, grow them forward in time, and then again, run FSim on it. So in that way, we're trying to get an idea of looking at things about how do fuel treatments, how effective are fuel treatments over time, and kind of what's the long-term effects of the treatments. Okay, so finally putting it all together. So for scenario evaluation. So for a given landscape, on the previous slide, I showed what would we have for a single landscape, or for one management scenario for a single landscape. So land managers might be considering several treatment scenarios, as you can see here. And so basically, we'd run all those treatment scenarios through this framework. We come up with different results, different probabilities. One of these could be the baseline scenario. And then land managers can use the outcomes from these different scenarios to kind of get an idea of whether or not these scenarios are not only achieving their land management objectives, but are they producing less smoke in the long run? And then can they use that as part of the justification for local communities for increasing prescribed fire in current day? And so on to the final slide. I just wanted to say what's next. In the following presentation, Laurel Sindewald will give a demonstration of how this framework can be applied to inform land management decisions. I want to note that this project's partially funded by the Bipartisan Infrastructure Law, Investing in America Inflation Reduction Act. And I'd like to give a special thanks to Shawn Mandel at the Center for Computational Mathematics at Colorado University in Denver for generously providing us additional computational resources for running FSim. Yeah, he really saved us on this. So thank you, Shawn, and thank you everyone for your attention. And now Laurel, we'll get to the main event here.
Awesome. Thank you so much, Shawn. All right, let me go ahead and share screen and get all set up. Hi, everyone. So I'm Laurel Sindewald. Again, I'm an ORISE postdoctoral fellow working with Karin Riley and Shawn Urbanski, as well as Rachel Houtman, all of whom you've heard from in this session. Also Chris Eckerson, who's another ORISE fellow on the team. So following Shawn's presentation, I'm going to zoom in on our study area, Okanogan-Wenatchee National Forest, and I'll show you some preliminary results using this emissions estimation framework. So Okanogan-Wenatchee, or Oka-Wen for short, is one of 10 initial priority landscapes identified by the Wildfire Crisis Strategy. Oka-Wen and surrounding forests include 6 of 10 high-risk firesheds in Washington state, and the central Washington region attracts 3.5 million visitors a year. This tourism is dependent on healthy, accessible forests and is heavily impacted by wildfire evacuations and smoke. Oka-Wen encompasses traditional lands of many First Nations east and west of the Cascade Crest, including those of the Confederated Tribes of the Yakama Nation and the Confederated Tribes of the Colville Reservation. So the Central Washington Initiative was formed to plan and implement treatment scale-up on a 2.5 million acre landscape, including Oka-Wen. The initiative was awarded an initial $102.6 million in funding for work through 2024 with an aim to scale up treatments to 35,000 acres a year. So to this end, CWI has formed partnerships with NGOs, governmental organizations, and the Yakama Nation. The photo here is from a workshop we held in Wenatchee last May to meet with people from Oka-Wen and representatives from the Central Washington Initiative. And thanks to their hard collaborative effort, CWI was able to complete over 35,000 acres of treatments in fiscal year 2024. But you'll notice far fewer acres of prescribed fire were completed. This is in part because of regulatory hurdles managers face in implementing prescribed fire on the landscape. At the workshop, we spoke with Okanogan fire and fuels managers and even got the chance to take a field trip to a site where they had done a broadcast burn in the previous year. Because of extensive ecological departure from historical stand species composition and structure, managers implement treatments in a cadence, completing mechanical treatments and piling fuels before burning the piles, and only then doing broadcast burns or maintenance prescribed fire. Pile burning is easier to accomplish from a regulatory standpoint because the dimensions of the piles help managers to quantify the number of tons burned, and also burns less than 10 feet in diameter, so they don't require written permission. They fall under rule burns. Burns of more than 100 tons in a day are subject to additional regulatory oversight by Washington DNR and approval based on meteorological conditions and wildfire risk. Ultimately, broadcast burning is needed to reduce wildfire risk and rectify ecological departure. However, snow restricts broadcast burning to late spring through early fall. Fire weather during the summer fire season precludes broadcast burning for several reasons, including escape risk, manpower, and desired burn intensity. And by the time fall rolls around, the surrounding communities are thoroughly fatigued by smoke impacts from the fire season. Inversions are also more common in the spring and fall, and smoke tends to pool in the valley bottoms where people live. So the upshot is that managers have maybe 6 days that are suitable for broadcast burning in a given year. Managers are then in a position of trying to thread a needle to rising to the mandate of the wildfire crisis strategy to scale up treatments, but facing significant constraints with respect to one of the most powerful tools with which to do so. So we're aiming to apply our decision support framework to Okanogan and simulate different management scenarios with increased prescribed burning, for example, to estimate potential savings in terms of fewer large smoke events from wildfires and reduced wildfire risk to communities. In the process, we'll create a daily geospatial database of emissions risks for the region that Shawn outlined in the previous presentation, which can be used for future smoke transport modeling work, hopefully. So I have some preliminary results to show you today. So you've already heard a lot about FSim, the large fire simulator, and Shawn described our framework really well. So I'm going to go through the methods very quickly and in the most basic level. So we delineated fire occurrence areas, regions where FSim will ignite fires based on pyromes delineated by Karin Short et al. At the Fire Sciences Lab, and level 3 ecoregion boundaries. So each of these FOAs have different fire regimes and, importantly, weather. So FSim is limited to a single weather stream for a given FOA, so it's important to constrain model runs to relatively smaller areas. As a quick recap, FSim has 4 submodels: ignition, weather, fire spread, and fire suppression. Ignition, weather, and fire suppression are all stochastic, based in part, the first 2 on historical distributions of fire locations and dates associated with weather conditions. So after a run, FSim outputs the fire parameters as well as CSV files with information about locations, dates, and weather conditions for every fire. And fire spread is deterministic based on Rothermel's spread equation and Scott and Reinhardt's adaptation of Van Wagner's crown fire initiation model. So why do I emphasize that? Well, once we've run FSim once, we can use the outputs to hold all the stochastic components constant and rerun the same fire events on a new landscape. So for the preliminary results I'm showing today, we ran FSim with the 2016 landfire landscape and then reran the same ignitions with the same weather conditions on the 2020 landfire landscape. So any changes should be attributable to the landscape itself versus stochasticity in the model run. So here we can see landscape changes or disturbances in the form of mechanical treatments, commercial and non-commercial, thinning, and prescribed fire. A very small portion of the landscape was treated between 2016 and 2020, but 5.4% of the landscape was impacted by wildfire. I selected 4 analysis areas to narrow in on regions of the landscape where prescribed fire and other treatments were concentrated, as well as areas where wildfire occurred. So even still, you can see they represent small portions of the landscape. Moving on to some results in the interest of time, we can see here that the burn probability raster for the 2016 landfire FSim run. Our analysis areas vary from relatively low burn probability in the black to burn probabilities around 0.12 or 12 years out of 100 in analysis areas 3 and 4 with those bright areas there. The histograms on the right show distribution of pixels for burn probability values in each analysis area. The burn probability distributions in the analysis areas have similar shapes for 2020, but the axes have shifted. Karin pointed that out with one of her earlier presentations. So notice now that the maximum burn probability on the landscape is 0.073 as opposed to 0.12. So an overall decrease there in the maximum burn probability. So subtracting 2016 from 2020, we can better see changes in burn probability across the landscape. In some cases, there appear to be increases in burn probability. More on this in a minute. If we overlay the MTBS wildfire parameters and treatment polygons, we can see that they correspond with declines in burn probability, though not always, like as in the case of area 2, which has uniformly low burn probability regardless. The black crosshatch polygons are the wildfire parameters, and we can see right away that they tend to match with declines in burn probability, such as in analysis areas 1, 3, and 4. Okay, so these histograms show distributions of mean changes in burn probability by treatment type. I created a 1 kilometer buffer around treatments and wildfire parameters as an approximate distance of treatment effect based on some of Karin's previous work. And I found the mean of every treatment or wildfire polygon, and then plotted the distributions of these means and calculated 95% confidence intervals. The effects attributable to the treatments at the landscape scale are pretty negligible, even if they are technically significant. The largest effect, as might be expected, was attributable to wildfires, so a decline of 0.006 between 2016 and 2020. So that's a 5% decline relative to the maximum 0.12 to help conceptualize that. The prescribed fire category includes pile burning, so this may account for the very small additional decrease in burn probability risk, given that commercial and non-commercial vegetation treatments precede pile burning in that treatment cadence we looked at earlier. So recall that FSim also outputs flame length probability rasters. We burned all TreeMap pixels in FFE, the fuel and fires extension, to get the amount of fuel consumed at each flame length. And then we multiplied that by a PM2.5 emission factor and converted the results to kilograms per acre. So if we multiply the probability of a pixel burning at a flame length by the amount of fuel consumed by the estimated emissions and add the results for each flame length category, we get expected emissions. So for these preliminary results, we only had we could only calculate expected emissions for forested lands. Those are covered by TreeMap. We use fuels data from the separate FuelMap imputation Karin talked about earlier. So for future work, we will include all of the rangelands in the study area. Expected PM2.5 emissions declined for 52% of forested pixels and increased for 18% and was unchanged for 30%. We would expect some increases in expected emissions in areas that were previously disturbed and are recovering, but 18% is pretty high. So we think this may be due to changes Landfire made between 2016 and 2020 to improve representation of fuel models based on community feedback. Even though there wasn't a full remap between 2016 and 2020. So we can see that most of the pixels for which emissions increased were in undisturbed areas. So all the gray here, or white, pixels classified as undisturbed in both 2016 and 2020. Very few fell into other disturbance or recovery categories, the colorized pixels elsewhere. Zooming in, for example, on analysis area 1, fuel models changed for about 69% of the pixels in this analysis area, and this was pretty typical for all 4. So you can see, like, it's covering a wide portion of the area. And these changes corresponded roughly to increases in burn probability on the landscape. So That's not to say that the fuel model changes were inadvisable. We might assume that they represent the landscape better since they incorporate on-the-ground knowledge, but we can't take these increases in burn probability or expected emissions at face value. To investigate the relative contribution of treatments and wildfires to the decline in PM 2.5 emissions on the landscape, I clipped the pixels that showed decline in emissions by the treatment polygons. The percents indicate the percent of pixels that had declining emissions that fell within the within 1 kilometer of a treatment or wildfire. Treatments were actually responsible for a larger proportion of the change in emissions, though the wildfire pixels showed a reduction in expected emissions by a greater amount more frequently. So this is the mean reduction in 2.5 emissions across the different categories with a 95% confidence interval. So our preliminary analysis here was somewhat scuppered by the updates made to Landfire between 2016 and 2020. So we can try this again with 2020 to 2022. But fewer treatments occurred in Okanogan during this 2-year period versus the 4-year period, hence why we started with the former period. But even in the 4-year period examined here, very little prescribed fire was implemented, and much of that was pile burning. Broadcast burning has been severely limited by those regulatory constraints. So we look forward to using our framework to simulate treatments at a broader scale in FBS using FIA data imputed via TreeMap. We will be able to simulate changes in expected emissions associated with the increased scale of treatments executed and the future treatments planned by the Central Washington Initiative based on our discussions with them, as well as different hypothetical scenarios where maybe more broadcast burning is possible. So we hope that this work ultimately will support managers in Okanogan as they continue to thread the needle of facing the wildfire crisis while constrained by smoke. Thank you very much. I think we have a minute, maybe a little less for questions. All right, well, if there are no questions, thank you all very much for joining the session. And that concludes this session for today. Please feel free to reach out to presenters if things occur to you. Thank you all so much for tuning in.